Hi, this is Rawa from Chem 112, and today I'm going to be talking about the molecular orbital of the F2-1 and the F2+1. So the F2-1 consists of two fluorine atom. Um, we know that fluorine has a 7 valence electron, so I'm going to start with drawing the the atomic orbital of the fluorine on the left. It has 7 valence electrons, so we have 2, 4, 6, and 7. And this extra electron is caused by the negative charge of this fluorine. The one, and we go to the fluorine atom on the right, which is a neutral, so it has 7 valence electrons. We're gonna be having in the middle the molecular orbital of the molecule, the F2-1, which consists of two sets of orbital. One a lower in energy, called the bounding orbital, and one is higher in energy, called the anti-bounding orbital. The bounding orbital, we call it like sigma, like sigma 1s for this level, and the anti-bounding electron we refer to it as a sigma star, so we add a star. So how are we gonna be adding the electron in these two orbital level? We're gonna be having one electrons from each atom at a time, like one from here and one from the one on the right, one from one on the right and one from the one on the left. The second love, the 2s, is just the same as the 1s. The most complicated one is the 2b level. So since the fluorine has a small interaction, small 2s and 2bx interaction, so the sigma comes first. That's why we have sigma. The sigma comes first, and then we have the bi orbital. We have here the by 2by y and the by 2by, and the anti-bounding orbital are just the mirror view of the bounding pair. And we're gonna put each electron from each atom, one from the right and one from the left. And here we have the molecular orbital of the F2-1. So moving on to the F2+1 molecule, the molecular orbital are just the same. It's just the same as the F2-1. The only difference is that the plus charge right here, which means that's one of the atom that are bonding has an electron shortage, which I have over here, the one on the left. So the fluorine has 7 valence electrons, so here's 2, 4, 5, and 6. So there's one missing right here that goes by the plus charge over there. Let's keep this in mind while filling in the 2b orbital. But the question is, why do we need the molecular orbital diagram? Why do you need that? Because that the electron in the atomic orbital represents specific atom. However, in the molecule, the electrons are rearranged in a way to represent the whole molecule, not just one atom. It represents the whole molecule. So after we drawing the molecular orbital diagram for both Fe2-1 and the Fe2+1, let's go and calculate the bond order for both molecules, which calculated using the equation half the number of bonding pair electron minus the number of the anti-bonding pair electron. So starting with the F2-1, which is half, the bonding pair electrons are 2, 4, 6, 8, and 10. So 10 minus the anti-bonding electrons are 2, 4, 6, 8, and 1, 9, which is 1 over 2. Moving to the F2-1, which is half, the bonding pair electron are the same, 2, 4, 6, 8 and 10, and the anti-bonding electrons are 2, 4, 6, and 1, 7, which is 3/2. So what does that mean? What does that mean? That means as the bond order goes down, the bond length goes up. So that means the bond order of the F2-1 is longer than the F2 plus 1. That also give me a clue about the strength of this bond. So since the bond order is down, the bond strength should be up, should be down. So that means the F2-1 bond is weaker than the F2 plus 1. So that means since the bond order is weaker, the F2-1 is weaker than the F2 plus 1. That means the F2 plus is more stable than the F2-1. They both exist, but F2 plus 1 is more stable. So this is the molecular orbiter for the F2-1 and the F2 plus 1, and we draw in the bond order, the bond length. Hope you enjoyed this video. Thank you.